Hello, dear students. I am Rina D. Mendoza, and I will be your teacher for today. Our most essential learning competency for this week is to compare the relative wavelengths of different forms of electromagnetic waves. Specifically, describe the transmission and propagation of EM waves. But before we proceed with the lesson, let's have first these following key concepts. First, we have the electromagnetic wave or EM wave, also known as the EM radiation, is a disturbance that carries and transfers energy through a field. Electromagnetic wave transmission is the act of transferring or sending energy from one spot to another, while electromagnetic wave propagation is the means in which waves travel to transfer energy. We also have electric fields and magnetic fields. Electric field is a vector quantity whose direction is defined as the direction that a positive test charge will be pushed when placed in the field. Thus, electric field direction is always directed away from the positive source charges and towards the negative source charges, as shown in the diagram on the right. A magnetic field, on the other hand, is a vector field that describes the magnetic influence on moving electric charges, electric currents, and magnetic materials. Magnetic fields are produced by electric currents that can be macroscopic currents in wires or microscopic currents associated with electrons in atomic orbits. Magnetic field lines around a long wire, which carries an electric current, form concentric circles around the wire, as shown in the diagram on the right. The direction of the magnetic field is perpendicular to the wire and is in the direction the fingers of your right hand would curl if you wrap them around the wire with your thumb on the direction of the current. This is known as the right hand thumb rule. When you were in grade 7, electromagnetic waves were already introduced. And now that you're in grade 10, we will deepen your understanding about this concept. To start with, let's take a look on this chart. Are you familiar with this? Very good. This is known as the electromagnetic spectrum or the EM spectrum. The EM spectrum is the range of frequencies of electromagnetic radiations with their respective wavelengths and photon energies. These waves can be categorized as low-frequency waves and high-frequency waves. The low-frequency waves consist of radio waves, microwaves, infrared, and the visible light, while the high-frequency waves composed of UV radiation, X-rays, and gamma rays. In the electromagnetic spectrum, what have you observed on the arrangement of the wavelength and their frequency? Very good. As you look on the EM spectrum, from the radio waves to the gamma rays, the wavelength is decreasing while the frequency is increasing, right? This only shows that the wavelength is inversely proportional to the frequency. With this, we can observe that the radio waves have the longest wavelength and it's about the size of the buildings, while the gamma rays, on the other hand, have the shortest wavelength and is around the size of an atomic nuclei. Remember, all electromagnetic waves transmit photon energy, and this energy is dependent with frequency. Thus, frequency is directly proportional to the energy of the waves, which means that a higher frequency wave transmits greater amount of energy than lower frequency waves. Therefore, EM radiations with very high frequency, such as gamma rays, can carry very sufficient energy that can be beneficial and harmful to the living things and the environment. But, have you ever wondered how are these waves transmit and propagate? During 1800s, the concept of electricity and magnetism was given emphasis by different scientists. But it was on 1870 when James Clerk Maxwell, a Scottish physicist and mathematician, made the theory that a changing magnetic field produced electric field, and a changing electric field produced magnetic field and oscillate perpendicular to each other and to the direction of the propagating wave. He also showed in his mathematical equations that the speed of propagation of electromagnetic wave is identical with that of light, thus revealing light, according to Maxwell, is connected with electricity and magnetism. The predictions and proposed equations of Maxwell were not yet scientifically accepted until a German physicist, Heinrich Hertz, proved Maxwell's electromagnetic wave theory to be correct and accurate in 1888. In his laboratory, he generated and detected electromagnetic waves through experiments. The discovery of electromagnetic wave led to the development of radio waves or Hertzian waves. Because of his discovery, the unit of frequency of waves, which is equal to cycles per second, was named as Hertz in his honor. And now, let us discuss on how Heinrich Hertz showed the electromagnetic wave transmission and propagation. Heinrich Hertz was the first to transmit and detect EM waves through a setup which is made up of radiator and resonator. In his experiment, a high voltage current was applied to the two ends of the two metal wires, which generated a spark in the gap between them. This spark resulted radiation of EM waves. These EM waves traveled through the air and created a spark in a metal coil which is a meter away. And if an LED is placed between the gap, the bulb would light it up. This was a perfect evidence of EM wave propagation and detection. All waves differ in terms of productions and properties, but they have common features like transmission and propagation. Based on Hertz's experiment, electromagnetic waves are produced by the vibration or oscillation of an electric charge Q. The frequency of electromagnetic wave is equal to the frequency of oscillation of this charge. This vibration creates a wave which has both an electric and a magnetic component. An electric field E and a magnetic field B are transmitted through the space while oscillating alternately. These oscillating electric and magnetic fields regenerate each other as the wave propagates outward through space. The electric field and the magnetic field are mutually perpendicular to each other and traveling in space to generate electromagnetic wave. And the direction of propagation of the wave is perpendicular to both electric and magnetic field, which means that in a 3D model, if the wave propagation is in x direction, the electric field is in y direction, and the magnetic field is in the z direction. This phenomena makes electromagnetic waves as transverse waves. All of the electromagnetic waves carry and transport energy through a vacuum at a speed that is equal to 3 times 10 to the 8 meters per second, a speed value commonly represented by the symbol letter c, known as the speed of light, which is the product of wavelength and frequency. To further understand the propagation of electromagnetic waves, let us differentiate the propagation of mechanical waves and electromagnetic waves. Mechanical waves require a medium to propagate, while electromagnetic waves do not need a medium at all. The media used for mechanical waves are solid, liquid, and gas, but it is not capable of transmitting energy through a vacuum or space. Electromagnetic waves, on the other hand, can travel not only through gas, liquid, and solid materials, but also through vacuum or empty space. The sound waves, seismic waves, and water waves are examples of mechanical waves that need a medium to transport energy, while radio waves, visible light, and UV radiation are examples of electromagnetic waves that can travel through a medium and as well as in a vacuum. For us to clearly understand the lesson, let's perform the activity on electric field and magnetic field. For the direction, draw and describe in the box how an electromagnetic wave propagates in an empty space. Use red pen for the magnetic field and blue pen for the electric field. Label the parts and draw an arrow for the direction. And now, let's answer the activity. The vibration of electric charge creates electromagnetic wave. This wave has electric field E, represented by blue ink, and the magnetic field B, represented by red ink, which are transmitted through the space while oscillating alternately. In the diagram, the wave propagation is in x direction, the electric field is in y direction, and the magnetic field is in the z direction. In this activity, the direction of propagation of the wave is perpendicular to both electric and magnetic fields. So remember class, electromagnetic waves are transverse waves in which the oscillation is perpendicular or 90 degrees to the direction of the movement of the wave. It is not only in one dimension, we also have electric field and magnetic field that are perpendicular to themselves. With this, we have oscillation that are both perpendicular to the direction of the motion of the wave and the corresponding fields. These waves are disturbance that carry and transfer energy and propagate or travel in anything. They can travel through a medium like light which can move through water, or radio waves which can move through the walls of our house to hear the sound from the radio. But they can also move through the vacuum or space, like the UV rays and the visible light of the sun that travel in space to warm and give light to all the planets like the Earth. And that ends our lesson for today. Did you understand it very well? If not, you may go back to the lesson presented in your module. If today's lesson is clear to you, congratulations! You may now answer the exercises in your module. Good luck! But if you are still confused and want to know more, you can check out on the following references.